Okay, I guess we might as well get started here. So welcome everybody to another round of the GLOSOLAN FAO Soil and Water Pollution Training Sessions. My name is Nathan Park. I'm a soil and water pollution consultant for FAO. I'm going to be covering today, this afternoon, and Friday sessions for Christoph. um, Today we're going to start this morning with the determination of pH in soils. Chris Van Hoof from Vito will be giving the presentation today. If anybody has any questions, please feel free to raise your hand, drop them in the chat, or speak up. We'll try and give plenty of opportunities for discussion back and forth. And yeah, with that, we might as well get started. So Chris, please take it away.
Good morning, everyone. My name is Chris van Hoof. I'm working at Vito. It's the Flemish Laboratory for Environmental Monitoring in Belgium. I'm working in the analytical laboratory and I'm a senior researcher in the inorganic laboratory. Today we are going to discuss the determination of the pH. A little bit the outline of what we are going to discuss today. First of all, an introduction, why we are going to measure pH in soil, a description of the analytical methods, the principles, the overview of available standard methods, and the influence of soil extraction solutions, and also the dilution factors. Then a little bit theoretical background about pH measurements, about the structure of a pH electrode. Then we go to the practice to describe the analytical procedure, how we determine the pH in the soil, some quality control protocols that we apply and are necessary to perform a good pH measurement, and some health and safety issues. First of all, what is pH? I think everyone knows that's an indirect estimate of the hydrogen plus concentration or the hydrogen activity, like it is called, in pure water or a salt solution. And it's a very important parameter to characterize the general soil conditions. How do we measure the soil, the pH in the soil? It's dependent, we do an extraction with a liquid extract, and it's dependent on, of course, the liquid soil ratio, the type of extractant. We have defined different extract in the procedures. You have water, you have calcium chloride, and you have potassium chloride. And of course, the measurement technology, which pH electrode you use, and so on. Why is the soil pH so important? It gives you an idea also about health, the conditions of your soil. First of all, it has an impact on your nutrient availability, as the pH levels affects the solubility of essential nutrients in soil. So different nutrients are more readily available to plants at specific pH ranges. If these pH ranges different, also the availability of your nutrients can change. In slightly acidic to neutral soils, we're talking then about a pH between 6 or 7. Most of the nutrients are accessible for plant uptake. So it's very important for the nutrient availability that you have a neutral pH in the soil. It also impacts the soil microorganism activity. It has an impact on this, and it is related to the bacteria, the fungi, the earthworms. And these components play a crucial role in the nutrient cycling and in the organic matter decomposition. And also the pH has an impact on the soil structure. You need a proper pH balance for a good soil structure because that allows a better water filtration, a better aeration, and a better root penetration. So it's very important that the soil pH is at a neutral condition to perform a proper soil, a healthy soil. Recently, the state of the soils in Europe, a report was published by ERC. Below, you can see the reference, and you can always, later on this publication will get publicly available. You can put on the link and check the report. And in the report, it was stated that in Ukraine, approximately 24% of the soils are acidic, so more to the lower pH range. On the right side, you see a map of the soil pH, but measured in water in the European Union. Unfortunately, Ukraine is not included in this map, but it's nevertheless discussed in the report. They describe also that the soil acidification was particularly present in the neutral areas of the Polisia zone. I think you better know than me where this zone is allocated. And there they have identified significant issues. So it's important also in the Ukraine to monitor the pH in soil. The report also describes that soil acidification is not only a Ukrainian problem, but it's a global concern because it has an impact on the soil quality, on the ecosystem integrity, and on, of course, also on the human well-being. And especially non-cancerous soils are affected with low buffer capacity, and that's leading to a decline in the pH. So we avoid this decline in the pH because, as I mentioned before, this can have an impact on the nutrient availability, and also the more acidic soil become, then there is a decrease in the mobility and also in the availability of the toxic elements, and that we also want to avoid. In the report, it is mentioned that acidification is a significant issue in Ukraine, but also in Turkey. And also this has an effect on the agricultural productivity and the environmental quality. The drivers of this soil acidification that include, of course, natural processes, but also industrial emission and, of course, the agricultural practices. It is stated that the more use of ammonium-based fertilizer, the more this leads to a soil acidification. This is a short introduction why the soil pH is so important to measure. If we're gonna look to the analytical methods that are available to determine this pH in the soil, then we see the basic principle that is described in all the procedure is that first of all, you do a sample pre-treatment. The soil is air dried or dried at maximum 40 degrees C, and then passed over a sieve of a mesh size of 2 millimeters. That is generally applied over all the methods. Subsequently, you do an extraction of the soil in the aqueous solution, and this solution can differ. You can use water indicated as the pH water, or you can use 0.01 molar calcium chloride, or you can use 1 molar potassium chloride. These three methods are often described in the different procedure that we have available. And the salt to solution ratio, it differs also between 1.5 over 1.2.5. And sometimes they take care of the mass volume ratio, otherwise sometimes volume to volume ratio. That are the difference that we observe between the different methods. And of course, subsequently, the pH is measured in the suspension. If you are going to look to the standard methods that are available, we always rely on the European standard methods and the ISO methods. The EN ISO method 10390, this covers the soil treated biowaste and sludge, and it is described the determination of the pH. This standard is a merger of the ISO standard of 2005 and the European standard of 2012. They are both combined because they are covering the same matrices, especially also the soil. So this standard is also recently revised so that the newest technologies are described in this ISO standard. The second method that we have available is the INSOP method of the GLOSOLAN, describing the standard operating procedure for soil pH determination. And then we have two Ukrainian methods who described first the hydrolytic acidity and the second one, the exchange acidity. Maybe have a closer look to the different methods. First of all, the European ISO method 10390. Also here, the sample pre-treatment is air dried and sieved over a sieve with a 2 millimeter mesh size. And then we have three methods described for the pH determination. First of all, the water, then the potassium chloride, and then the calcium chloride. In blue, I already marked the difference between these methods. Here you have a 1:5 dilution. You will see later on that it differs, and we always work with the volume-volume ratio. Later on in the other methods, often a mass to volume is applied. This gives another dilution factor in the determination of the pH. In the method, it's described that at least 5 milliliters of sample is taken, and then you shake or mix the suspension for 6 minutes using a shaking or a mixing machine so that you get good contact between your extraction solution and the soil. You wait then for 1 hour, and then you measure the pH before that the 3 hours is passing. The pH calibration and the measurements are done at room temperature, so at laboratory temperature are applied to have a stable measurement. And the measurement of the pH in the suspension is measured while being started or immediately after. That is the method that is described in the EN ISO. If we are going to look to the GLOSOLAN method, then are quite similar procedures. Only the blue, only the things that are marked in blue are different. Here you have for the water extraction a different extraction ratio, and they all work with mass volume ratio. What is also different in the method for the pH water, they describe that they stir the suspension for 10 seconds before taking the pH measurements. And that for the pH gas, potassium chloride and calcium chloride, the electrode is placed in the unstirred supernatant. So there are some difference if you stir in advance before the pH measurement or not. Important is that you have a good equilibrium and that the measurement is stable over time. Also here the measurements are performed at room temperature, and also this sub-procedure contains some quality controls that are generally applied. I will come back to that later on, but here the slope of the calibration has to be between 95 and 105%, and the offset has to be between 0 and 30 millivolt. But I will come later back on these quality controls aspects. If you're going to have a look to the determination of the hydraulic acidity according to the Ukrainian method, here you do an extraction in 1 molar sodium acetate solution. So that's totally different extraction. So we didn't discuss this procedure further because then you get a totally other results that you obtain. But if you have a look to the other Ukrainian method, this covers better the procedure that we already described in the ISO and the GLOSOLAN method. Also here you do an extraction in potassium chloride or in calcium chloride. And here the 1/2.5 dilution factor is applied with the weight to volume ratio. Also here you do an extraction of the soil sample. Here is 30 gram defined, but if you keep the dilution factor described in the method, you come similar methods. Also here you shake with a mixer for 1 hour and you measure the suspension pH. They do also a step further and describe the filtration with sodium hydroxide to calculate the exchange acidity. But this is normally not done in our laboratory. We see that different extraction solutions are described and what are the difference in results of the pH when you use another extraction solution. First of all, if you extract with water, then implies a dilution of the soil solution, and it's the reflection then of the actual pH in the soil solution. You don't get any interaction with the soil particles at that time because most of the protons tend to remain at that moment fixed to the soil particles and are not released to the soil solutions. That's why often we don't do the pH determination in water, but in calcium chloride or potassium chloride. If you do the extraction in calcium chloride, then you then you get extra salts into the solution, and the presence of these salts in the solution masks the effect of varying soluble salt concentration in the salt samples, because the calcium chloride solution exchange the hydrogen ions from the soil for the calcium ions in the electrolyte, and this results in a lowering of the measured pH value as compared to the pH water. So for the pH water, the pH will be higher than for the calcium chloride extract pH measurements. If you go then a step further and apply the potassium chloride extraction, then the soil pH in the potassium chloride, it measures the acidity of the soil solution as well as the reserve acidity that are in the soil colloids. So you extract more hydrogen ions from the soil because you get an exchange of as well the hydrogen as the aluminum ions that are present in the soil particles. So for the pH of the KCl, of the potassium chloride solution, will be lower than the pH of a water. This is of course sample dependent, but it can differ between 0.5 to 1 pH units, but it's sample dependent. We have done in also our lab previous different extractions on the same sample. And in here, the sludge, 2 sludges are evaluated and 2 salts are evaluated. The blue bar represents the results of the pH in water. The second one, the pH in calcium chloride, and the third one, the pH in potassium chloride. And then you can see for some the effects that it has. You can see always the water has the highest pH, while for the calcium chloride and the potassium chloride, the pH decreases, especially also in the soil sample. So that's the impact of a different extraction procedure. What about the extraction ratio? If the ratio between the water and the soil increases, then you get an increase in the pH, but it's not straightforward. It's not linear that it takes up, because there are other effects that take place. If you get a dilution of the soil, then of course you get an increase in the dissociation of the hydrogen plus ions from the soil surface, and also an increase of the amount of hydrolysis of the aluminium ions. And both of these effects help to buffer the solution, and that's why the pH remains rather stable over a wider range of the dilution in acid soils, and it is not an linear increase like that. In soils where there is a higher pH, you also get hydrolysis of the basic cations, and also these give an impact on the pH, and you get a more stable pH with dilution. So as you can see in the figure that was described in the methods of soil analysis, then you can see if you have a 1-to-1 dilution, a 1-to-5 dilution, and then up to a 1-to-10 dilution, so that you could see it has not a linear impact. And here the difference in pH is only 0.1 difference. So it has a limited impact if you get a dilution, different dilution factor. So that is a little bit the description of the analytical methods. Are there already some questions about this issue before we go to the theoretical background?
Nothing in the chat, but if anybody has anything, please ask. It looked like the European methodology uses a soil volume, not mass.
Yeah.
That seems inaccurate and difficult to measure. Do you just use a graduated cylinder, or what do you do about different soil
I will
textures?
show it later. We use a spoon where we know exactly that it contains 10 milliliter of sample, and we have defined it before, and we use that spoon to define it. So, but I will show it later in the presentation.
I imagine, depending on the soil texture and density, there's can be quite a bit different mass per sample.
Yeah. And that can have an impact on the dilution ratio, but it has limited impact. So I think the differences are 0.1, 0.2. It's not that quite the impact on the final pH results.
Yeah, and I suppose these pH measurements are really ranges, so it doesn't really matter if your pH is 7.1 or 7.2. It's just kind of
Yeah, if you take a new subsample, often you get already these differences. It's already included a little bit in the differences with the sampling and the measurement itself.
Anybody else have any questions or comments before we proceed? Okay.
Okay, then we can go further to the theoretical background. A little bit of theory behind pH measurement. The definition of the pH measurement, of course, is a measure for the acidity or the alkalinity of a solution, and that at a given temperature. And it ranges between 0 and 14. And it is, according to Sørensen, described as the pH is the minus logarithm of the concentration of the hydrogen plus ions. And it comes from the ion product of water, as the dissociation constant describes, that the hydrogen plus and the hydroxide the ions over water describes the dissociation constant, and the product of the hydrogen plus concentration and the hydroxide minus concentration is 10 to the minus 14, and that is also the scale that is used for the pH value. If the hydrogen plus concentration is equal to the hydrogen minus concentration, then we have a concentration of hydrogen plus of 10 to the minus 7. And then you have, of course, a neutral solution. So then you obtain a pH of 7. If you lower the concentration of the hydrogen plus, of course, you can see that you lower the value. And the pH sensor is nearly linear over the 14 decades. Maybe the further theory that I'm going to present, or the source that I use, or the theory source that is described by the Metrum and by Mettler Toledo. Those are two manufacturers that offers a lot of pH electrodes and instruments. So you can always refer to that for the further information. How to measure pH? Of course, you need a tool which is sensitive to measure the hydrogen plus ions that define the pH value. And it is composed of two electrodes. First of all, a measurement sensor, which contains a glass membrane at the bottom, which is sensitive to the hydrogen plus ions and also observes the reaction between the glass membrane and the sample solution. The second one is a reference sensor, and that it's needed to supply a reference signal or a potential for the pH sensor. So you need a combination of both, because the potential difference between these two electrodes is used to determine the pH value of the measured solution. You call it all, in the figure it is presented, that is there are the two half cells. So it's here the reference electrode, the pH electrode. These are both immersed in the sampled solution, and you measure an electrical potential between both the references. The reference electrode, it has to produce a stable potential independent of the concentration that is in the solution, while on the other hand, the pH sensor, so the measurement electrode, is equipped at the lower sides with a glass membrane, and that takes care of the hydrogen plus ion measurements and the change also in hydrogen plus ion concentrations. Now it is presented as two half cells, but in practice, most of the time, we already work with the combined pH electrode, while we see here the different parts in the reference electrode. So you have your reference electrolyte, your silver chloride cartridge, your diaphragm, and on the other side in the pH electrode, the sensitive glass membrane. They are now combined in one electrode. Up here is the silver chloride cartridge of the reference electrode, the diaphragma, and the glass membrane. I will come back to the different parts later on. Also here is at the bottom, you can do a refilling of the electrolyte, and it is all protected by a glass shaft. We are going to measure a potential when we do a pH determination, and this potential is linear, is a linear function of the hydrogen plus concentration in the solution, and it's defined by the Nernst equation. So you measure a potential which is equal to the potential intercept. It's a stable factor, and you measure at different points the potential, but all these are constant factors which are all summed up and are defined by the potential zero. Later on, you have the slope, which contains a few factors where R represents the real gas constant, T the temperature, which is an important factor because here you define that the pH is temperature dependent. So that's important to know, and I will come back to that later also. Z is the valence of the ion, and F is the Faraday constant. And then, of course, the logarithm of the activity or the concentration of the hydrogen plus ion, which represents the pH. So this is a linear calibration function that you see. As I described, you have a measuring electrode where at the bottom there is a glass membrane. And this glass membrane is composed of a hydrated layer. It's shown in here. And this glass membrane is immersed into the solution. If you have an acidic solution, then the hydrogen plus ions will move inside this layer. On the other hand, when you have an alkaline solution, the hydrogen plus ions will move out of the layer. And then when they move out, you get a negative potential. If they come in, you get a positive potential. As the inner electrolyte is a stable solution where you have a stable pH factor, then the potential difference between the inner layer and the outer layer, then you get a potential difference, but is a measure for the pH value. It's important that this hydrated layer is kept wet, and therefore you have to store your pH electrode in a suitable storage solution. You also may not touch this glass membrane with a tissue or so to clean, because you then can damage this glass membrane. Also, this glass membrane can be attacked by alkaline ions like lithium, potassium, and sodium, because they are going to interact as a hydrogen plus ion. And then the alkaline ions, then you measure a lower pH value than actually present. So that it's called an alkaline error that you have to take into account. If you want to measure alkaline solution, then you have to select a proper pH electrode that is capable to handle these alkaline samples. That's an important issue. Over here, you see an electrode, the basic electrode with the membrane glass, which contains the internal buffer and the platinum lead of wire. But it's for a single application, it's not a combined electrode. Then besides the measurement electrode, you have the reference electrode. And in the reference electrode below, you have a diaphragm or a junction that they call it. And that's the connection between the reference electrolyte and the measuring solution. And this has to be stable because it's used as a reference signal to measure the pH value. So if you see in the figure at the left side, you see the electrode solution, and there you can see that the electrolyte, there is an outflow to the sample solution, and it is important to get correct measurements. The outflow of the electrolyte is needed to have a constant diffusion potential, and so that you can use it as a reference signal. But important to know is that the electrode has to be filled with enough electrolyte. In this right side for the picture, you see that the electrolyte is below the sample level, and then you get not a proper measurement with the pH electrode. So you also have to avoid that this diaphragm is blocked or something, because that can have an impact on your signal, and then you get a deviated pH result. So the diaphragm is important that you have an electrolyte exchange, and also it's important that it is open so that the exchange is performing very well. There are different types of diaphragms. A rather standard one is a ceramic porous junction, and it's suitable for water samples that are very clear, that there is not because it's easy in use, and then you get no blockage. You will see it on the figure on the right side. Here you can an exchange of the electrolyte, and they can be released so that you have a stable signal. It's not suitable for more difficult samples because if there are more particles inside or something from the soil, for instance, then you can a blockage of the diaphragm and then you get an error in your pH measurements. What is often applied is the sleeve junction, and then the electrolyte comes out of the electrolyte via a hole, which is covered then by a circular ground glass or a plastic sleeve, as shown in this picture. Also in this picture, you can see here the release of the ions by different methods. It's commonly applied because it's a fixed and flexible design. Also, we have noticed that it is a reproducible electrolyte outflow, and it's not so easy blocked by particles, or you get also more stable signal. In the reference electrode, we also have to add an electrolyte to get a stable signal. And the reference electrolyte, you have besides electrolyte also the reference element. And it's a silver chloride element that is applied. And in standard, the reference element, it's a silver wire that is coated with silver chloride. And then as electrolyte, 3 molar is the saturated solution of potassium chloride is used with the addition of silver chloride. But if there are temperature changes, you can offer formation of silver chloride particles, and that block the diaphragm. And therefore, it's better to use the new technologies that are commonly applied more and more. And there they use, instead of this configuration, they use a small cartridge, which is filled with silver chloride particles. And so these chloride particles can provide the silver ions for the chemical reaction at the leaf-off wire. So this cartridge contains also enough silver chloride for the full lifetime of your electrode. So you don't have to don't do anything maintenance on that electrolyte system. As reference electrolyte, here only saturated potassium chloride is used, and then no silver chloride to be added later on. This is a figure of the combined electrode as we see it. We have discussed already, you have your measurement electrode, you have your reference electrode with the different parts, and this is combined. It's a glass, most of the time a glass cover with inside the reference electrolyte. Here is the silver ion trap as I just discussed. Here is described with a ceramic junction, but it can also be a sleeve junction. Most of the time also a temperature probe is integrated because the pH measurements are temperature dependent. And then you can always measure the temperature at a time at the pH measurement. And you have the pH sensitive glass membrane. So that's the combined electrode with all the different functions. How to select a pH electrode? Of course, the proper selection of a pH electrode, because you can have different setups, is depending on the characteristics of your sample, depending the temperature, the pH range, the consistency, have to be measured supernatants where there are soil particles inside. So it's the application for which you want to use the pH electrode that define which electrode you're going to need. Because I have described already that you have different diaphragms and junctions. There are also different glass membranes, the more circular one, the more cylindrical one, the flat ones. And also these are defined depending on the application. You have some universal use of glass membranes that allows a low alkali error that covers high pH values and high temperature. Otherwise, you can select also pH electrode with fast response times for weakly buffered solution, for low conducting solutions, or for non-aqueous solutions. These are all possibilities that are where you need a certain pH electrode. how you define which electrode is the best for your application, then it's best to contact your supplier of the pH electrode. They all have the list of the pH electrode they have available and for which application, because there are so much differentiation and each supplier has its own pH electrode. But they cover a little bit the same things, but the configuration can be slightly differently. We have now our pH electrode. How we can do a measurement? First of all, we have to do a calibration of the pH. When to calibrate? If you want a correct and precise result, you have to calibrate daily. A weekly calibration of for instance, it's not enough. You need a daily calibration when you start up. You have to calibrate. And you calibrate with 2 or multi-point calibrations and then using buffers and preferable certified buffers. I will come later back to that. For instance, we use in our lab pH 4, 7, and 10 to set up the calibration. The calibration is also temperature dependent, so you always have to do a temperature measurement so that you can do the proper corrections for that. And you work with automatic buffer recognition. I think in the newest system, it's included. Otherwise, you have to adapt it manually, but it's better to include it already, the automatic buffer recognition. And that means that you, depending on the temperature, your buffer concentration, the theoretical value will exactly defined. Of course, your pH value that you want to measure have to lie within the calibration range that you set up. A little bit more to the buffer solutions. It's very important that you select the proper one, that are high quality standard solution, and that you know exactly the pH values of these buffer because you're using these buffer for the calibration. As I already indicated, that the pH buffer is also temperature dependent. It's important to record the temperature always during a measurement. Also, do not use buffer after expiry date because the buffers can degrade. And it's also important to use fresh buffers when you set up a calibration, especially for the higher pH, because at the higher pH, the buffers have the intention and also the samples to incorporate CO2 into the solution. So then this can have an impact on your pH value. It's also encouraged to measure the buffers and the samples at equal temperatures, because then you have the same effects that playing a role during the measurement. And if you have used the buffer for the measurement, don't to throw it away and don't use it again or keep it like that, because the buffer value can change over time. A little bit more about automatic buffer recognition. If you have in your system an automatic buffer recognition, then these buffers are in the software of your system, and they contain tables which is defined for that buffer, and at that temperature, then there's a theoretical buffer defined. For instance, a pH 4.0 at 25 degrees differs a little bit at 20 degrees C. And then if you have an automatic buffer recognition system, then the system automatically will correct for that. Of course, you have to have a temperature sensor that is connected so that you can automatically correct for this value. If you set up a pH calibration, then you have as I told before, the NAS equation, and you set up your potential against to your pH, and you set up a calibration curve, and ideally the curve will situated here on the blue line, which means that your offset, it's the potential at the 0 and null value, is located over here. Ideally, the potential at 0 is 7. It's then the pH that is ideal. Of course, in practice, you get a slight differentiation in that, and you get an adjustment of that. And it is expressed in millivolts that is defined, and according optimal, they say your offset has to be within plus minus 50 millivolt, which correspond to a pH between 6.8 and 7.2. As we see in the GLOSOLAN method, they allow even an offset between 0 and 30 millivolt. Both are applied 15 and the 30 millivolt. If you want more accurate results, you allow the 50 millivolt, so it's defined by that. Besides the offset that you are going to evaluate, you also look to the slope, what's also important. Ideally, your slope is the black line, and it's a slope that is a theoretical value that the slope is at a pH of 24 degrees C, but it's because it's temperature dependent, minus 59.16 millivolt per pH unit. In practice, this slope can differ a little bit, and generally applied, they allow an optimal slope between 95 and 103%. It's also important that you evaluate this according to the same temperature. If you measure at 20 degrees C, if you apply automatic temperature correction, then it will be by your system itself corrected to the 25 degrees C and compare it to the theoretical curve of 25 degrees C. And that's why also the slope is expressed in percentages instead of absolute value, because the absolute value is temperature dependent. In GLOSOLAN, the slope is defined between 95 and 105%, but it's almost the same as the optimal that they propose. So the pH calibration, you always check the offset and you check the slope, and that's the indication if your pH electrode also work properly, yes or no. If these values deviate, then your pH electrode is also decreased, and the lifetime of your pH electrode comes to an end if these values are not fulfilled anymore. As I told before, this has an influence. The pH calibration is influenced by the temperature. The middle blue line is the linear line at 25 degrees C. If you increase in temperature, you will get a higher calibration line. If you get lower in temperature, it will lower. So it's defined in the formula by the Nernst equation where it describes the temperature dependent. That's why you can correct for the calibration line, because the temperature is defined and you can correct for that. If you see for the influence of the temperature, you can have two influences. First of all, it can have an influence on the sample. So you can measure the different pH values at different temperature in the sample, depending on that configuration. And for that, you cannot correct. You cannot correct for the measurement into the sample. If the solution is cold or warmer, you cannot correct for that. That's why we always encourage to measure the samples and the calibration at the same temperature. If there is a few degrees Celsius difference, it's not an important, but it's critical that you do it at a similar temperature. On the other hand, the influence of the temperature on the slope, for that you can correct. And that's automatically corrected by the pH meter. Of course, if you have a temperature sensor available and that you measure simultaneous with the pH measurement, also your temperature measurement. So that is quite a difference that is important to understand, that you can correct for the slope, but you cannot correct for the temperature in the sample. This is already also a table that shows you what has the impact of the temperatures and the slope. For instance, this is an example given a temperature at 24 degrees C, you get a slope of 59.60, while at 45 degrees C, that's already high temperature, you get a slope of 63.12. So you get a difference of 4 millivolt, and that can have an impact on your pH value. That's why it's important to do the automatic temperature compensation. Finally, when you don't do a pH measurement, you also have to see that you measure at the moment that your signal is stable. And that's indicated by the drift. When you put your sensor in your solution, the pH value will drift still a little bit. And at a certain point, it becomes constant. And that is the point that you define. In generally, you describe the drift between 0.1 and 2 millivolt per minute. The lower the value, of course, the longer the measurement can take, but the more precise the result is. But if you take it between 0.1 and 2 for both pH measurements are very good to do that. It's also important to have a proper response times that is not too long. If the response time is too long, it's also an indication that your electrode degrades and that you have to do some changes on that. How to maintain the electrodes, it's very important that you do it properly because it extends the lifetime of your electrodes. So after the measurement, you have to rinse electrode thoroughly with deionized water. If you are just using a water solution, flush it, but never clean the glass membrane with the tissue, just flush it. Also, if you have an electrode with an electrolyte that you have to fill, it will be, the plug is open during the measurements. It's needed to get an electrolyte flow at the bottom of your electrode, but at the end you have to close it because otherwise always the electrolyte will flow out of your electrode during storage. So you have to adapt that. And it's important to place your electrode in a proper storage solution. What is the best storage solution that you can have? It's a little bit of conflict between the glass membrane and the diaphragm. The glass membrane prefers to have deionized water to keep it fast, while the diaphragm needs the electrolyte solution. But these potassium ions, of course, can degrade the glass membrane and indicate and results in an aging of the glass membrane. So often the suppliers also offer a potassium-free storage solution so that you have no aging of your glass membrane and that you also prevent the growth of fungi. So this solution is used for all combined pH electrodes. Also often still the potassium chloride saturated solution is used as reference electrolyte, and it's also used as a storage solution. So always take care when you have a pH electrode that you check what your manufacturer described for storing the pH electrode, because that really extends the lifetime of your pH electrode. So this is the theoretical background. Are there questions about this part of the section?
No, brought back lots of memories from over a decade ago, working in the laboratory with. When was the last time this thing was calibrated? Why is this storage solution all dried up? I feel like they're very can be finicky machines.
Yeah. Mm-hmm.
Anybody else have any questions or comments, experiences in their lab?
Yeah, it's a lot of theory, but I think it's interesting to know how to work the pH electrode, what things you have to consider, and how you have to store the electrode or handle the electrode. I think it's important to know to do later on in the lab the practical measurements.
Yeah, I can remember them being quite delicate, and I guess this is the only instrument you have other than the extraction. So
Yeah.
if you let it get really out of whack, then you
Yeah.
can mess up a lot of measurements down
Yeah.
the line.
Yeah. You cannot make a lot of errors only on the pH measurement itself.
Yeah, yeah. Okay, well, if nobody has anything else, that's all right. I guess we can well, we're approaching what, 12:45 now?
Yeah.
Do you think we have time to take a short break
Yeah, I
for that?
think it's good to have maybe for a short break.
Sure, let's do it's 47 right now, so let's come back in 5 minutes. So we'll come back in I don't, you guys are in different time zones, so at 52, and we'll start again here in 5 minutes.
Okay,
Okay?
perfect.
Okay, thank you. Oops, I just said all of that with my microphone muted. Everybody okay? Back from break? Any questions they came up with while they were grabbing a drink of water? Okay, nothing. Let's go ahead then, Chris. Let's finish off the second half, and yeah, please go ahead.
And now coming to the analytical procedure, that will be easier to explain also is the handler. That is what we do in the lab, and that are the things we have to perform to do a pH measurement. First of all, I rely on the European method, the ISO method, because that is a method that we apply in our lab and from which I can demonstrate also some results. but they are quite similar with the other methods. First of all, we do a sample pre-treatment, air dried or dried at maximum 40 degrees C, and we pass the soil sample over a sieve with a 2 mm mesh size. This is the way how we perform it, and you get a very tiny soil sample to analyze. Here you see the spoon that we have available where we can measure the 10 milliliter. We work always with a test portion of 10 milliliter of soil, and we know if we completely fill this spoon and we scrape it off, then we have 10 milliliter of sample. We add it in a tube where we can also, this is already the tube that we can place in our pH carousel in our sample plate to do the measurements so that we don't have to change from a recipient. So here we have the soil added. We add then the extraction with 1 mole potassium chloride, and that we do in a ratio of 1/5 volume. So this is 50 milliliter of 1 mole potassium chloride solution that we have. We always take care that we get a good interaction between the soil and the potassium chloride. So we shake already a little bit with the recipient so that we get a good contact between both parts. Then we close the recipient over here. We did it with the paraffin foil, and then we put the beaker onto a shaking machine, and then we shake. Here you can see the frequencies that we use, and then you will see that you get also get a good movement or solution that it can get in contact so that with the soil, so that you can create an equilibrium between both parts. We shake for 60 minutes. We leave then the sample standing for at least 1 hour without shaking, and we analyze then the pH within the 3 hours. This is from our software system, the different steps that we apply during the measurements. This is an example of a manual procedure. We can also do it with an automated procedure that we can take part of the sample plate. And then you have more additional trees that define the different models that have to be performed. Because if you use the sample plate, you always have to define that you go to the next samples, that you have to flush your electrode. That is done automatically. But this will be shown later on when you have the on-site training in the laboratory. So what I described, for example, here in the manual procedure, you take your sample, you stir for a moment, you do that for 15 seconds, then you set your stir off, and then you measure the pH. And in the next train, it's defined that you do the calculation of your pH value. It's calculated out of the potential that you have measured. You report it, and you put all your data in a database. And that's how it is defined in the software of the instrument. Also here, it's an example of the signal drift that we always state at 2 millivolt per minute. You always have to measure at least 10 seconds, and we define that after 120 seconds, he can stop and or do the pH measurement. That we have a measurement between 10 and 120 seconds. And here it's also that the reference temperature is here defined as 25 degrees C. But more details about the software and all will be presented during the on-site training. What we do in the lab, first of all, this is an example of the electrode that we use. We have here used an electrode with a gel electrolyte and not a liquid electrolyte. It's also a gel electrolyte of potassium chloride saturated. And here is the glass membrane that you see. This is a temperature sensor. You can use a separate one or one that is included in the pH so that we can measure the temperature together with the pH measurement. You can see here the buffers that we use for calibration. It's the pH 4, pH 7, and pH 10. And we also work with automatic buffer recognition so that can be applied when the temperature is measured. In between measurements, if we use the automated procedure, the electrode will always be flushed so that you don't get a contamination between the different samples. When we have set up the calibration, we also always do a verification of the slope and the offset. As I stated previous, that the slope we define as criteria that the slope has between 95 and 102% of the theoretical value, and the offset has between pH plus minus 0.25. It corresponds with a difference in voltage of 50 millivolt. And you can see here an example of the calibration curve that we obtained, the measured pH values, the millivolts that are the term, the temperature we are measured, and the time of seconds that we measured, so at least 10 seconds. And then the slope is calculated, taking into account the temperature corrections, of course. So we have a slope of 98.7%, that's very good. And we have a pH 0 at 6.867, which also fulfilled the rule of the offset. And that is shown by the software. You can so directly see if your calibration fulfills the needs that you require. A second thing that we do is a verification of the calibration, and then we measure independent buffers. It's pH 6 and 8, and we follow that up. You can see here it's our sample plate, the different calibration standards, and here the independent standards that are measured directly after the calibration, and we allow the deviation of 0.1 pH unit. We follow that up, that it's always within that factor, so that you can rely on the pH measurement you do on the samples further on. We always measure at lab conditions, about 20 to 25 degrees C is often applied. That's also stated in the GLOSOLAN procedure. We do the stirring just before the measurement. When the stirring has done, then immediate after we perform the pH measurement. You can see when you do soil sample, you measure the supernatant, and it's not a clear solution. You still contain some soil particles. That's why you need a robust electrode that can handle also soil particles, so that your diaphragm is not blocked during the measurements. What you have to report, you have to do no calculation, because you cannot take into account any temperature correction of your soil sample. So what you report is, of course, your pH results at 0.1 pH unit. The temperature you measure, it's important to mention that, because that can be an influence on your pH in the sample. Always mention which medium you used for making the suspension. For us, it's always pH potassium chloride. And of course, the reference to the method that you applied, or the standard that you applied. That are normally the things that we include in a test report. We have now covered the measurements that we done on the laboratory. But for pH, it's often measured on the field. That it's not in the soil, but then in the groundwater that we measure the pH value. But they apply the same principles. They only need other equipment. They use a portable instrument where they can measure the pH, and often also combined with the conductivity, because both parameters are most of the time defined in the water sample. You use also a proper electrode. That are electrodes that are suitable to use on the field, so that they are robust electrodes. This one that we use in our laboratory contains also a built-in temperature sensor, and it has a fiber diaphragm. It's a nylon fiber net that they used for that, and it has also a gel electrolyte filling. It's all selected to have a practical use on the field. Also, this pH electrode is calibrated with the 4 buffer standards. And also, you have to define the type of buffer, so that the system automatically can use a temperature correction. Therefore, it's also important to use certified buffers, or buffers that are recognized by your system. Instead of using the buffers out of a bottle, we often work in bags that contain buffers at a certain pH, but that can be used only once. So that are bags that are available. We will show it later on also in our laboratory to show these bags that are used for the calibration. We also do an independent control with pH 6 and 9, and also for that, bags are available with buffer solution at that pH value. The use of this pH electrode and measurement instrument will also demonstrate it during the on-site field training. And this is given in the module F2 on the 27th of November. And it's given by our Vito colleagues. And they will demonstrate also this application. Maybe some practical things that you have to consider when doing a measure and when you see errors, where are they coming from? An electrode is not performing well with these proposals that we can already define. If your membrane is dehydrated, so the glass membrane, or contaminated or damaged, you cannot perform a proper pH measurement. If your electrolyte is contaminated or missing, or there is not enough electrolyte available, that can cause an error. Also, you have to avoid air bubbles in the region of your diaphragm and on your membrane, so at the bottom of your electrode. You have to avoid that your diaphragm is contaminated, maybe by soil particles and so on, so you have to take care of that. And also avoid that you have a potassium chloride blockage at the outlet of your electrode. But by using a proper electrode that is a robust electrode, you can avoid this also. And of course, at a certain moment, your pH is out of specs, and then you have to remove it and replace it by another one. Some things to consider that can be applied wrong and that you have to adapt for. First of all, if you have an electrode with a liquid electrolyte, you have to measure with the filling hole where you add your electrolyte closed. Measure with filling hole open. It has to be open, and you have to close it when you are finished. I have to change that. Yeah, that's the wrong procedure. It's okay. The wrong procedure, if you have to close it, you have to open it, of course, during the measurement. You may never store your electrode in the ionized water, but in a concentrated potassium chloride solution or special buffer solutions for the electrode. You never wipe your glass membrane clean. You have only to flush it with water or another suitable agent. You may never exchange the electrolyte. You always fill and add additional electrolyte. Your calibration has been done daily and not on a weekly basis. And also, may not forget that temperature has no influence. Temperature has an influence on the pH result. It's also important to know. This is the analytical procedure. We are going to cover some quality aspects. We already handled that a little bit, but these are summarize a little bit what we did. Of course, what I described already earlier, it's important to verify the slope and the offset with specified target values, the slope in percentage of the theoretical value, and the pH, it's the offset that you control. Secondly, you verify the calibration by measuring independent buffer solutions. These can differ and can be also applicable on the pH range that you want to measure. What we also do is reanalyze these independent buffer solution if we run a batch of samples. After 10 samples, most of the time, 10 to 20, depending on how many samples we analyze, we remeasure the independent buffer solution. And we check if the deviation is not much more than 0.1 pH unit. And that's to verify that during the whole run, the whole analytical run, you maintain a good electrode and to check if this electrode is working still properly. So normally, if it's not fulfilled, you have to remeasure samples before the buffers that are not okay. That's a very important one, that you're monitoring constantly your quality of your pH electrode. This is an example of pH values of the buffers. This is buffer pH 6, this is buffer pH 8, and that we follow up in time. This is, for examples, for 40 measurement that we follow up, and we can check that the pH is within an acceptable range. It's the 2S border that you can see here, and you can see that these values are within that range. Also for the pH 8, also we see that it is a similar way going on, and that is during the measurements that we done, that everything is fine. Besides that, we also analyze some control samples. Because we are measuring in a 1 molar potassium chloride solution, we always measure the blank also from that solution as a control. During an analytical run, we always analyze at least 10% of the samples in Duplo to check if this is also okay. And the Duplo analysis not only include the pH measurement, but also include the extraction. You start from the sample prepared sample, you take there an amount to the extraction and to the pH measurement, and that you do in Duplo. And these data can be followed up in a control chart. We also have in our lab a reference soil sample. It was one used for proficiency testing, and we kept that sample to analyze always together with the other samples in one analytical run. And that has to be a pH value for our soil sample of 7.5, and that we follow up over time. And besides that, we also participate to interlaboratory proficiency tests to verify if our results correspond also with the results of other labs. That should be normally the case. This is an example of multiple measurements of soil samples that we did. That was also that we have to analyze a lot of soil samples. And here we selected a soil sample with a pH value of 4.7. And here a soil sample with a pH of 7.4. And that sample we took over during the whole batch that we did then for the analysis over time. And then you can see that for both soil samples, we get pH results within a pH value, an absolute deviation between plus minus 0.05. So you can measure very accurately your soil sample as long as your pH electrode is working properly. We also did some analysis on Ukrainian soil, and also for that we did some Duplo analysis. And these are the Duplo results of the soil samples. For that, there are 5 results that we obtained. And here the value, most of the time it's 0.05 that you have, and this one is 0.075 or something, the absolute difference. So it's all the maximum 0.1 pH unit that you can see between measurement 1 and measurement 2. So that's very good for these soil samples. And the pH values of these soil samples were in the range between 4.5 and 7.5, in that range. So we always try to take and select some samples that cover the different pH values. About the participation to the interlaboratory proficiency test. Yearly, Vito organized these round-robin tests for the recognition for the Flemish laboratories. And it includes both the soil sampling and the analysis. So not only the pH measurement, but also the soil sampling. We do soil sampling for 2 applications. The first of all is already described in a previous model, and that is a sampling to conduct a soil research, a contaminated soil research. You take a larger amount, what is already presented, and the pH potassium chloride value that we determine there, together with the clay content and the organic matter content that we determine on that material, is then used to recalculate the Flemish soil remediation values for some metals in soil. So this has a totally different application than the application we do for the round-robin test. For the round-robin test, we do a sampling to follow up the soil quality and the soil fertility. And also there, a specific sample protocol is defined, and that is applied also in the proficiency testing. And what contains this sampling protocol? First of all, you go to the field. The point you have to measure, you remove the top layer, you remove the roots, the organic remains of the plant, so that you really take sampling of the soil itself. And then you sample the layer between 0 and 30 centimeter using a coach auger with a diameter between 30 and 20 millimeter, and that in a specific pattern. Usually a cross pattern is defined, as this is shown over here. And we take over the cross 15 sampling points. It's distributed over the cross that the 15 sampling points are taken. And it's also prescribed in our method that the GPS data logger is used to register the sampling points so that we can later on check which pattern is taken in this sampling procedure on that field, and that it's verified that it's taken properly. That is during the proficiency test, this is also controlled. We have to supply these data and then they verify if the sampling is taken on the good proper way. Then the sampling come to the lab and we do the analysis. These are the results not only from Vito, but from all participating lab in the results. And it are results from 2017 up 2023. The blue and yellow bars represent the pH value, and the red bar is the right axis, and it represents the relative standard deviation. The blue bars are results obtained on the reference samples. It means that here the participant didn't do the sampling, but only did the pH measurement on the reference samples. While the yellow bars, this is the soil sampling is also included. So the participant do a soil sampling, pre-treat the sample, and then do the measurement. And as you can see over time, the pH value difference between about 5 to 8, but the relative standard deviation in most of the time is less than 4%. Only once here there was a relative standard deviation of 6%. So labs can do it, even including the soil sampling, do it in a very proper way, that the deviation between all the lab results are within maximum 6% and most of the time 4%. As you can see, there is not a lot difference between including the sampling, yes or no. So the sampling is also very much under control. That is all about the quality aspects. Maybe some small later part. pH measurement are not that toxic one, but nevertheless you have to take care. You work in a laboratory, so you have to take care of your personal safety. And what is regularly done is to wear a lab coat, to use safety glasses, and to use gloves. If you are handling the source, we always wear gloves. For the sample pre-treatment, we also encourage to wear a mask so that you don't inhale the dust sample. For the chemicals we use, we always verify the hazardous properties, and that is, we check the specific material safety data sheets. Of course, for pH measurement, these are limited. Even if you look to the chemical hazards, especially for the buffers at the high pH, you have to avoid inhalation and skin-eye contact. Also for the potassium chloride, it is described that you have to avoid inhalation and the skin-eye contact, and that it can also cause violent reactions with strong oxidizing agent. That are the things you have to consider when to do a proper measurement and to work on a health and safety condition. To conclude, but I've given out the presentation more the theoretical aspect, the principle of the procedure, the different steps that we have applied in the procedure. A next step will be a dedicated and specialized on-site training to have a look to the practical aspects. And that will be given in the module L1, and that will be given for group 1 on Monday, the 25th of November in the morning, and for group 2 on Tuesday, the 3rd of December, also in the morning. So, and then we will go more in detail to the practical aspects, to the measurement system, to the software, and then you can see also the electrodes we are using and so on. Okay, thank you for listening.
Thank you. Anybody have any questions? I don't see anything in the chat. I can think of one. So what happens if your duplicate analysis of pH fails in one of the batches or is outside of the limits? What happens there?
If it fails, we redo it often. And we also check the sample, the initial sample, to check if it looks heterogeneous, yes or no. But it's a repetition of the sample. If the duplo is not okay, you cannot have a lot of influence on it, but you can check what can be possible causes of that to do it. If there is a reason, maybe an extreme pH value that can also, if you can see in your original samples more, although you sieve it, that you see really inside. But although the fact that your intake, it's about 10 milliliter or like that, you still have a representative amount of the soil sample, so that has to be less impact normally. But
Does the whole batch get redone? Like, do you have to redo the whole? Like, you're doing what, 10%,
we
one in a
normally
penny?
don't do that a whole batch as long as we see that the buffer verifications are okay. Then you
Or
can
okay,
say the measurement is okay. But often if we report the results, then we often mention it that we see that there, or we report the Doppler results, that we see that there is a higher deviation and that we mark it in the reports.
okay.
It's
Yeah,
all
it seems
done
procedurally. Oh,
every
sorry. Go ahead.
deviation that you see, you mark it on your analytical report.
Yeah, I feel like pH is probably this one of the more simple
Yep, yep,
analysis to confirm, but probably the most important parameter impacting
yep,
all sorts of things, being contaminants, metal uptake,
yep.
yeah, fertility, but probably the most important,
Indeed.
analysis.
I think in the soil sample, the pH together with the total organic carbon content are two
Mhm.
important parameters in the soil health aspects. Uh, yeah.
Yeah. Okay. Any other questions from anybody, or are we good? Okay. What we'll do then is I think we'll meet back in about 2 hours and 45 minutes to go over some groundwater sampling techniques. So we'll talk to everybody in a little bit here. Thanks, Chris. Appreciate it.